Now let's look at the second step in the efficient coding transform of binocular signals, gain control. This is after the input signals are decorrelated into the summation signal and the difference signal in blue axis. The gain control is to multiply the summation signal by a gain G plus and the difference signal by a gain G minus. This will not change the direction of the blue axes, but will stretch them or shrink them, and the probability distribution of these data, these signals will then also be shaped, stretched, and shrinked accordingly. Then the transformation from the input is now the combination of decorrelation K0 and the gain control G. K0 being this coordinate transform and G is this diagonal matrix. And the output then O plus O minus, combining these will contain both the input noise, although the input noise also goes through the gain controls, and the encoding noise. And no gain control is the case when the gains are equal to 1. And the output power would just be equal to the signal's power plus the noise power, including both the input noise and encoding noise and not. The extracted information, and it will be determined by the signal to noise, obviously, the signal being this one and the noise being that one. And this is always less than the amount of information already available at the input stage where the encoding noise and is absent. And so this is just the usual. You can never extract more information than what's available at the input stage by any encoding. And of course, when you have the gain control, then the signal noise changes both by the gain to the signal and the gain to the input noise. When the gains are so big, it can be so big that the encoding noise is almost negligible. Then you can extract almost as much information as what's available at the input. So therefore, increasing the gain will increase the extracted information amount, although at the same time you are also increasing the cost of the output power, since the stronger gain makes this cost higher. We can plot out the information extracted on the vertical axis versus the output power cost on the horizontal axis, and their relationship is nonlinear by a log function. Before the gain control, the output power for this difference in channel is quite weak, and the extracted amount of information is not that much either. And the power on the summation channel is much higher and also extracting more information. However, as this curve slowly saturates, the more you spend on the power, in the end, the return is diminishing. So therefore, if you can apply gain control now, expanding the power on the difference in channel from a small amount to a larger amount, then you can also gain substantially on the amount of information you can gain. At the same time, if you shrink down the power of the summation channel from a larger amount to a smaller amount, you can save a lot of power without losing too much of information gained because of the saturating curve. Our objective has this trade-off between the cost coming from the horizontal axis and the information gain from the vertical axis, and with lambda as the Lagrangian multiplier characterizing the trade-off between them. And this cost comes from the summation of cost from the two channels, summation channel and difference channel, and the information is also the summation of sum of the information from the two channels. Because the two channels are decorrelated, they are not redundant information, therefore you can add it together for the total information. Therefore, this becomes a sum of two trade-offs. Each is a trade-off in one channel. One is a summation channel trade-off, one is a difference channel trade-off. Each is a trade-off between its own cost and its own information. So therefore you can write the objective for each channel. This objective depends on GK, the gain in that channel, which has its own cost term and its own information term. You can see that this information term for each channel comes from this formula for the information, other than this lambda. Okay, this lambda comes from that lambda, so we can just ignore that. So this is the same as that. Therefore, our objective is a sum of two objectives, one for each channel. This is the summation objective. This is the difference channel objective. Each objective can be optimized separately by finding the optimal GK. Okay, and it is the one that satisfies this equation, or equivalently satisfying that equation for each channel separately. So we can optimize each channel separately, and you can do it as an exercise to find a solution for these, and you can find this is the solution. And it can be simplified into two essential factors. One is the smoothing factor, and the other is the decorrelation factor. Therefore, we just get this GK and put it into this gains. And this is how we do the gain control step for the efficient encoding.